Hello, everyone. I'm Chenglong from Temple University. Today, I'm going to present our paper, HAWatcher Semantics-Aware Anomaly Detection for Appified Smart Homes. Smart home IoT devices are long known to be vulnerable and unreliable. Anomalies that happen on them can cause severe damages in the physical world. For example, in case A, the room gets flooded because the command that closes the valve gets lost. And in case B, a broken relay inside a smart plug can prevent it from cutting off the power supply. If this smart plug is connected to a electrical heater, this can cause fire. And in case C, an attacker can maliciously unlock the front door by injecting a spoofed presence on event. Targeting this problem, there are a lot of existing solutions. Most of them are using machine learning-based method. They train their model using event logs and then use the model to detect anomalies. Because they do not use any semantic information, so they need a large amount of data for training, and also they cannot or they have difficulty to capture complex patterns of smart home device systems. And also their generated model are black box models. So that means they are explainable. And also their model produce a large amount of false alarms. Our idea is device states are correlated with multiple semantic channels. Events and the states of one device can affect multiple other devices in the same physical environment. For example, when the user is back to home, he will open the door, which automatically turn on the light according to smart apps. And also, the motion sensor in the living room will detect active motion at the same time. To incorporate semantic information into anomaly detection, we need to answer three research questions. The first one is, what semantic information can we use for anomaly detection? In this work, we summarize the semantic information in smart home environment into three channels. The smart app channel stands for the home automation programs and user configures home automation rules. These rules and programs explicitly defines the home the correlation among the involved devices. The physical channel comprises the meaning of devices' physical attributes. For example, a switch is potentially correlated with a power meter according to our common sense. And finally, users' activity status can also serve as a good source of semantic information because the user can operate any devices manually. For example, when the user back to home, his presence sensor will turn to present, and which predict and after which the door will be opened and the lock will be unlocked. After we locate this semantic information, the next question is how to capture and represent semantic information. Semantic information from different channels is diverse and has different formats. To solve this problem, we propose the uniform representation of semantic information in the form of correlations. The semantic information are used to infer possibly correlated device pairs. And for the smart app channel, we use code analysis to interpret smart app source code. And in the physical channel, we apply natural language processing on the description of device attributes so that we can automatically discover possibly correlated devices. For example, the common sense of the power between the power meter and the switch. And finally, for the user activity channel, we use the motion and presence sensors state event to indicate users' activities. For each of these pairs, we generate a set of hypothetical correlations by enumerating the values of involved devices. Finally, the third question is how to make use of the semantic information for anomaly detection. The hypothetical correlations that are generated according to semantic information are not necessarily true. For example, for this correlation, it means the illuminance can only be high when the light is on. This correlation is only true when there is no other light source, like in a small bathroom. So for the hypothetical correlations, we verify them with the events log to exclude those unreasonable ones. Finally, after we get the verified correlations, we can detect anomalies as violations of correlations. So this graph shows the procedure to detect anomalies as we mentioned in page 2. For case A, because there is no action and feedback event of the valve, so the water detected event inside this correlation cannot find the expected follow-up event. So the system will raise an alarm. And for case B, because the relay is broken, even after the switch is turned on, the heater can still consume high power. So this is inconsistent with the correlation, and there will be an alarm. And in case C, because the user is not really coming back, so there will be no contact open event following the spoofed presence present event. So this is another mismatch and will cause an alarm. We evaluate our proposed system in 4 real-world test beds, and there are 6 participants in our experiment. We conduct our experiment for 1 month, and we use 3 weeks for training and 1 week for testing. To evaluate the performance of our HAWatcher, on testbed 1 only, we generate 24 testing anomaly cases, which covers 6 steps. And the result is very satisfying. We achieved the average precision of 97.83% and the average recall of 94.12%. On the same dataset, also compare the performance of HAWatcher with 2 baseline detectors, the association rule mining and the 1-class SVM. Which represent the data mining based and machine learning based method respectively. As a result, show our HAWatcher significantly outperforms to other baseline methods in terms of both precision and recall. Especially, our HAWatcher greatly reduced the number of false alarms. As you see here, we only have 4 false alarms among 7 days testing. So this greatly improves the usability of the detection system because false alarms are always annoying. In summary, we are the first to propose the accurate and non-black box IoT anomaly detection system. And that has a satisfying performance of precision higher than 97% and recall higher than 94%. And both the system and the generated results are explainable. Then we propose to use semantic information from multiple channels for anomaly detection. This semantic information including the smart apps, devices' physical attributes, and the user's activities. And finally, we find a method to capture and represent diverse semantic information as correlations. We use code analysis and natural language processing to extract the semantic information into uniform representation. And finally, we use the hypothesis testing method to verify and filter the hypothetical correlation generated from semantic informations. And due to the time limit, I cannot cover all the content of the work. So if you want more details, you can refer to our paper. Thank you very much for watching this video. Now I'm ready to take questions.